Hello friends, today I am going to explain about optimal binary search tree. The Model 28 focus on introducing dynamic programming design strategy and applying it to problems to construct optimal binary search trees. The objectives of this module are to explain dynamic programming, to explain dynamic search tree, to explain optimal binary search tree. Dynamic programming. Dynamic programming is useful for solving multi-stage optimization problems, especially sequential decision problems 1, 2, 3. Richard Bellman is widely considered as the father of dynamic programming. He was an American mathematician. Richard Bellman is also credited with the coining of the word dynamic programming. Here, the word dynamic refers to some sort of time reference and programming and is interpreted as planning or tabulation rather than programming that is encountered in computer programs. Dynamic programming is used in variety of applications. Dynamic programming is used to solve discrete optimization problems such as scheduling, string editing, packaging, and inventory management 1, 2. Dynamic programming employs the following steps as shown below. Step 1. Given problem is divided into number of subproblems as in divide and conquer strategy. But in divide and conquer, the subproblems are independent of each other, but in dynamic programming case, there are overall overlapping subproblems. The recursive formation is formed of the given problem. Step 2. The problem usually solved in bottom-up manner. To avoid repeated computation of multiple overlapping subproblems, a table is created. Whenever a subproblem is solved, then its solution is stored in the table so that in future its solution can be reused. Then the solution are combined to solve overall problem. Next we are going to see about binary search tree. Binary search tree is a special kind of binary tree. In binary search tree, the elements in the left and right subtrees are each node are respectively lesser and greater than the element of the node. In the figure we are seeing a binary search tree. In this figure we can note that it is not balanced tree. On the other hand, this is a skewed tree where all branches are one side. The advantages of binary search tree that it facilitates of a search of a key easily. It takes on to search for a key in a list, whereas search tree helps to find element in logarithmic time. Often an element is searched in binary search tree. Let's assume the given element is x. Compare x is the root element of the binary tree. If the binary tree is non-empty, if it matches, the element is in the root and the algorithm terminates successfully by returning the address of the root node. If the binary tree is empty, it returns a null value. If x is less than the element in the root, the search continues. The left subtree, if x is greater than an element in the root, the search continues in the right subtree. This is by exploring the binary search property. There are many applications of binary search tree. One application is construction of dictionary. There are many ways of constructing the binary search tree. Brute force algorithm is to construct many binary search tree. Finding the cost of the tree. How to find the cost of the tree? The cost of tree is obtained by multiplying the probability of the item and the level of the tree. The following example illustrates the way of find this cost of the tree. Example 1. Find the cost of the tree is shown in the figure where the item's probability is given as follows. A1 equal to 0.4, A2 equal to 0.3, A3 equal to 0.3. In the solution, the cost of the tree is obtained by multiplying the item probability and the level of the tree. The cost of the tree is computed as follows. In the cost equal to 3 of 0.4 plus 2 of 0.3 plus 1 of 0.3 equal to 2.1. It can be observed that the cost of tree is 2.1. Next we are going to see about optimal binary search tree. What is an optimal binary search tree? An optimal binary search tree is a tree of optimal cost. This is illustrated in the following example. In example 2, construct optimal binary search tree for the tree items a1 equal to 0.4, a2 equal to 0.3, a3 equal to 0.3. Solution: there are many ways one can construct binary search tree. Sum of the constructor binary search trees and its cost is shown in the figure. It can see the cost of trees respectively 2.1, 1.3, 1.6, 1.9 and 1.9. So the minimum cost is 1.3. Hence the optimal binary search tree is figure 3. How to construct optimal binary search tree? The problem of optimal binary search tree is given as follow. Given a sequence of k equal to k1 lesser k2 lesser summation equal to k lesser kn of nth order key with a search probability p for each key kp. The aim is to build a binary search tree with minimum expected cost. One way is to use brute force method by exploring all possible ways and finding the expected cost, but the method is not practical as the number of trees as possible is Catalan sequence. The Catalan number is given as follow: C of n equal to 2n n 1 by n plus 1 for n greater than 0, C of 0 equal to 1. If the nodes are tree, the Catalan number is C of tree equal to 1 divided by 3 plus 1 of 6 tree equal to 5. Hence, 5 such trees are possible. In general, quotation of 4 power n divided by n power t by 2 different BSTs are possible with n nodes. Hence, alternative way is to explore dynamic programming approach. The idea is to one of the keys in a power 1 to a power n, say a power k, where n less than equal to k less than equal to n must be the root. Then, as per binary search rule, let left subtree of a power k contains a power 1 equal to a power k minus 1 and right subtree of a power k contains a power k plus 1 equal to a power n. So the idea is to examine all candidate roots a power k for 1 less than k less than equal to n and determining all optimal BST containing a power 1 equal to a power k minus 1 containing a k plus 1 equal to a power 1. The informal algorithm for constructing optimal binary search tree based on 1, tree as given as follow. Step 1. Read n symbols with probability pi. Step 2. Create a table C of I, j 1 less than or equal to I less than or equal to j plus 1 less than or equal to 1. Step 3. Set C of I equal to pi and C of I minus 1, j equal to 0 for all I quotation of n. Step 4. Recursively compute the following relation: C of I, j equal to C of 1 of k plus 1 plus C of k plus 1 equal to j plus summation n m equal to 1 p of m for all I and j. Step 5. Return C of 1 of 1 equal to n as the maximum cost of constructing a BST. Step 6. The idea is to create a table as shown in the below. The constructor table for building optimal BST. The The aim of the dynamic program is to fill this table for constructing optimal binary BST. What should be the entry of this table? For example, to compute 2, tree of two items, say key 2 key and tree, two possible trees are constructed as for shown in below figure and filling the table with minimum cost. And these are the figures, so that in figure 4 two possible base of BST for key and tree we can shown. Example tree. Let there be four items: A of Danny, B of land, C of Radha, and D of Z, with probability 2 by 7, 1 by 7, 3 by 7, 1 by 7. Apply dynamic programming approach, construct optimal binary search tree. The initial table is given in the table 1. It can be observed that the table entries are initial probabilities given. Then using the recursive formula, the remaining entries are calculated. Through this formula, we can calculate the dynamic programming. The updated entries are shown below in table 2. Similarly, the other entries are updated as follows. In C of 1, 3 and equal to minimum, so that we can calculate a minimum dynamic programming of this value equal to minimum of 12 by 7, 11 by 7 and 10 by 7 equal to 10 by 7. And next we want to calculate the C of 2, 4 and using dynamic programming we can calculate a minimum value and of 7 by 7. The updated table, through this value we can update the table in the table tree. The procedure is continuous, and we are going to see in the C of 1, 4 in the of minimum. The minimum value of the C, 4 is 12 by 7 through searching this, and it is also updated in the table 4 value. And it can be observed that minimum cost is 12 by 7. What about a researcher? This can be reconstructed by nothing the minimum k in another table as shown in table 5. It can be shown from the table 5 that C of 1, 4 is tree, so the item tree is root of the tree. Continuing this fashion, one can find the binary search tree as shown in the figure 5. Through this figure, it can be seen that the constructed binary values optimal and balanced. The formal algorithm of constructing optimal binaries is given as follows. Initialize the table for C. For I equal to 1 to 1 do C of I, I minus 1 equal to summation C of I, equal to P of I. N for C of n plus 1, n equal to summation. Initialize the table for R. For I equal to 1 to n do R of I, minus 1 equal to summation R of I, equal to I. N for C of n plus 1, n equal to summation. For diac equal to 1 to n minus 2. For I equal to 1 to n minus diac, do j equal to I plus diac. C of I, j equal to minimum. I less than k, less than or equal to j. C of I equal to k minus 1 plus C of k plus 1 j plus summation n m equal to 1 pm. Or I j equal to k, n for written C of 1, n. And complexity analysis. The time efficiency is summation n power 3 but can be reduced to summation n power 2 by taking the advantage of monotonic property of the entries. The monotonic property is that entry r of I comma j is always in the range between r of I comma j minus 1 and r j plus 1 j. The space complexity is of summa- summation n square as the algorithm is reduced to filling the table. Summary: in short, one can conclude the part of this model 28 that dynamic programming is an effective technique. DP can solve LCS problem efficiently. Edit: distance problem can be solved effectively by DP approach. Thank you for this opportunity. Thank you all.